Leveraging the digital certificates that we installed in the previous video, you and I are going to implement authentication of the IKE version 2 tunnel using RSA signatures. Let's begin. In our previous video, we implemented digital certificates on each of these routers. So now, armed with those digital certificates, if we want to, for IKE version 2 authentication, we could use the feature of RSA signatures instead of using the weaker and less scalable pre-shared keys. Now, one of the cool benefits of using digital certificates for the authentication piece is that we can also use that information from the digital certificates as part of our match statement inside of the IKE v2 profile. And to make that really flexible, we can use this really cool feature called a certificate map. Now, think about a class map just for a moment. What does a class map do for a living? A class map is simply identifying something or looking for certain types of traffic. Well, a certificate map does that same type of a function, except instead of looking at packets or certain types of traffic, a certificate map is set up to look for specific things in a certificate. So for example, we could create a certificate map that's looking for specific aspects of a certificate, such as the name. If we were looking for the name CBT Nuggets, as part of the name inside the certificate, we could say name, CO, which represents contains, CBT Nuggets. And then the really cool thing is, once we have this simple certificate map set up, we could use that as part of our IKE version 2 profile in the match statement. So check this out. We could say we want to match based on this certificate map, and then as R1 and R2 exchange certificates and they look at each other's certificates, if the name portion of those certificates contains CBT Nuggets, that will trigger the match statement, and that can make it very scalable, because we could have the hub, for example, with 70 or 80 remote sites. And if we're using RSA signatures for the authentication, the match statement in the profile on the hub could be used as a single profile, and that could handle all of the remote sites with one IKE version 2 profile. So as far as what's new is we're going to create this simple certificate map that says what we're looking for inside of the certificate that we received from a peer. We're going to say that we want to match on that new certificate map. And then we're going to change the authentication for local and remote from pre-share. We're going to change it to RSA Sig. The other item we're going to specify is that we're going to specify the trust point, which links to the CA server that we trust. And it's possible we might have multiple certificate authorities. We want to specify the CA that we're going to use to validate the certificates that we're receiving from the peers that are matching this profile. So when R2 sends its digital certificate over, R1 will say, okay, great, I'm going to use this CA's public key to validate the signature. And once R1 has validated R2's digital certificate, it can now trust the public key that was in R2's digital certificate that can then be used for the RSA signature verification that's going to happen between R1 and R2. And because we're using digital certificates for the authentication, we don't need to create any key rings, because we're not using pre-shared keys, and so the key ring doesn't serve any purpose if we're not using those pre-shared keys. Let's start off with a simple site-to-site tunnel between R1 and R2 using RSA signatures for the authentication. Now, a funny thing happened on the way to labbing this up. It's funny now, but it wasn't then. And when I started labbing this up, I usually walk through the lab a couple of times before I do it together with you, because I want to make sure everything's working correctly. And for the life of me, I could not get the RSA signatures, and I say that past tense, I couldn't get it working. I tried multiple IKE version 2 proposals, multiple IKE version 2 policies, multiple IPsec transform sets, multiple IPsec profiles. I tried it with a static interface. I tried it with a virtual template. I could not get it working. It took me the better part of 2 days, I kid you not, to find out what was going on. And it turns out that the key pair I generated on R1 and R2, I used a 2048, which should normally be no problem, that's fine. And it may be the version of iOS I'm using with the specific hardware I'm using. But regardless of the reason, it would not authenticate using RSA signatures if I was using a 2048-bit modulus in my RSA key pair. So what I did was, on R1 and R2, I removed the trust point. I zeroized the RSA key pairs. I regenerated them with a 1024-bit key pair. I re-authenticated, re-enrolled with the CA, and then the RSA signatures for authentication of the IKE version 2 tunnel, that started working. So I started working on this on Friday. It is now Sunday afternoon, and I suppose I could call TAC and dig into it. But again, this is not a production network, and again, it's very likely just a fluke based on the version of software and the specific hardware that I'm running this on. And then I thought to myself, oh my goodness, I'm going to be sitting here with you going through this, but if you went through the previous nugget with me, and you generated a 2048-bit RSA key pair, it's possible that you may have the same issue with using that key pair. So what you and I are going to do is we're going to go ahead and take it from the step that we left off in our previous video, and that is we're going to remove the trust point. We're going to remove the key pair, recreate the key pair, re-authenticate and re-enroll with the certificate authority, because I want to make sure that you see every step. So that in the event that you need to go to 1024-bit modulus with your RSA public-private key pair, you'll know the exact steps to do it. And then, once we're to the point where we have our digital certificates again, then we'll go into the IKE version 2 and we'll implement RSA signatures for the authentication of the IKEv2 tunnel. So the first thing we're going to do is we're going to go ahead and remove our PKI trust point. It was called trusted-CA. We'll simply put a no in front of that. It'll say, are you sure? We'll say yes, and now it's gone. Secondly, we're going to zeroize our public-private key pair, and the syntax for that is crypto key zeroize RSA, and it asks us, are we sure? And we type in yes, and now they're gone. Our next step is to reinitialize or recreate an RSA public-private key pair, but this time I'm going to specify a modulus of 1024, and I'll give it the same label I did previously, which is r1.cbtnuggets.com, regarding this new RSA public-private key pair. And next we'll put in all the information regarding our trust point, just like we did in our previous video. So crypto PKI trust point, the name of our trust point, the enrollment URL, the RSA key pair that we want to use, which is r1.cbtnuggets.com. We're going to include our fully qualified domain name of r1.cbtnuggets.com. We're also going to include as part of the subject name, common name R1, and organization is cbtnuggets.com. And I'm also going to specify that revocation check is going to be none. We're not going to do a revocation check. Next, we're going to go ahead and authenticate that trusted CA, which effectively says, I would like a copy of your certificate, Mr. CA server. So we'll say yes, we'll take it. And our next step is to go ahead and enroll, which is to request our own identity certificate. So we'll do crypto PKI enroll trusted-CA. I'm going to put in a password and confirm that password. Now I also want to make you aware that in the process of trying everything, I also tore down and recreated the certificate authority, but it turns out that wasn't the problem. And after trying multiple different changes with the CA, without any success, I put it back the way it was. So I'm not going to include the serial number in the certificate. I do want to include the IP address. So I'll say yes to that, and it's 15.0.0.1 that we'll include. And then we'll type in yes to request the certificate, specifically our identity certificate from the certificate authority. So now we're effectively at the same point where we left off in our previous video, with the primary difference is that we are using a 1024-bit modulus for our RSA key pair instead of the 2048 that we previously had. Next, we're going to create a PKI certificate map. The syntax is crypto PKI certificate space map. So in our certificate map, we could have 20 or 30 different entries, and it's going to process them in order based on their sequence number. In our case, we're going to have one entry. I just gave it sequence number 10. It really wouldn't matter if I put sequence number 1 or 50, because with only one statement that we're going to add, it's going to process that first, no matter what that sequence number is. Now, there's lots of things that we could match on in this certificate map. Now, just like a class map, looking for certain attributes of IP packets, for example, a certificate map is looking for certain attributes within a digital certificate. So we could match based on the subject name included inside of a digital certificate, or the issuer name, or the serial number, or an alternate subject name. So for example, if we said issuer name and then did a question mark, now as far as issuer name goes, the issuer in our lab environment here, the issuer name is ca.cbtnuggets.com. So we could specify EQ for equal and then type in ca.cbtnuggets.com, or we could type in CO, which means contains. Let's do that option. And then by typing in cbtnuggets, that's just a portion of that issuer name. So this certificate map, if we apply it somewhere, is going to have two thumbs way, way up for a match if it sees a certificate that is issued by a CA where the issuer name contains the string cbtnuggets. Next, let's create an IKEv2 proposal, and we'll name it IKEv2-proposal. How's that for creative? At least when we see it, we'll know exactly what it is. And remember, the proposal has three major ingredients. It's got the data integrity method, it's got the encryption method, it's also got the Diffie-Hellman group. So for this proposal, let's specify that for encryption, we're going to use AES 128, and for integrity, we'll kick it way down to SHA-1, and for Diffie-Hellman, let's use group 5. And that's kind of like the old school way of doing the Diffie-Hellman group and the hashing. And as long as we have compatible proposals on both sides for IKE version 2, we'll be fine. Next, let's create an IKE version 2 policy. We'll call it IKEv2-policy, And we'll simply say, okay, regarding the IKE v2 policy, we want to go ahead and link to the proposal called IKE v2 proposal, which has the list of the integrity, the Diffie-Hellman group, and the encryption that we're going to use. Next, let's create an IKE v2 profile, and we'll name it IKE v2-profile. And this is where we're going to specify the authentication method that we're going to use. So I'd like to think of the IKE v2 profile as the if-then statement, the match considerations, and then the authentication methods that we're going to do with a peer who matches that profile. Now, because we're using digital certificates, we can do a few additional little tricks here. For example, we can say for our local identity, we're going to use distinguished name, and that's going to get that distinguished name from our digital certificate. As far as matching the remote, we can use that certificate map. We can say match certificate and then the name of our certificate map. So if R1 is peering with R2 and R2 sends its digital certificate over to R1, if the issuer name of the certificate that R2 is sharing with us, if it contains CBT nuggets as part of the issuer name, that's going to be considered a match regarding this IKE v2 profile. And if we have that match, we then are going to specify that we want the authentication for both sides to be RSA Sig. So the syntax is authentication remote, RSA-Sig, authentication local, RSA-Sig. And we could authenticate one side using RSA signatures and the other side using pre-shared keys. We can mix and match. IKE version 2 allows us to do that. But in this case, we're going to use digital certificates and RSA signatures on both sides for the IKE v2 authentication. Now, previously, when we were doing pre-shared keys, we referred to the key ring right here in the profile. However, because we're no longer using pre-shared keys, inside of this profile, we do need to refer to the trust point that we're going to use to validate certificates. So to do that, the syntax is PKI trust point and then the locally significant name of our CA trust point. Next, let's go ahead and create a transform set. We're not going to use the default transform set or the default IPsec profile. So the transform set, we'll call it our-t set, and we'll use ESP, AES, and SHA for hashed message authentication code. And when we specify AES without a 192 or a 256, it implies it's AES 128. Next, we're going to create an IPsec profile. We'll call it IPsec-profile. And we're going to do two things. We're going to tell it what transform set to use with the set, transform set, and the name of our transform set that we just created. And we're going to set the IKE v2 profile using the syntax set IKE v2 profile and then the name of the IKE v2 profile that we also created. So this IKE v2 profile is this guy right here. And this transform set is this one right here. Now, as far as applying this to an interface, we could use the virtual template option, or we could use a tunnel interface. We've already done both of those options in this course. So for here, let's go ahead and simply create a static tunnel interface using interface tunnel 0. We'll use the IP unnumbered game once again. We'll say the tunnel source is E00. The tunnel mode is IPsec IPv4. The tunnel destination is R2's address of 25002. We'll apply the IPsec profile that we created with the tunnel protection IPsec profile and the name of our IPsec profile. Let's also include this interface in OSPF with the command IP OSPF1 area 0, and that's it for the configuration of R1. Now here on R2 we have the same issues with the 2048-bit modulus as far as the RSA public-private key pairs. So let's fix that first. We'll go into configuration mode. We'll say no crypto PKI trust point trusted-CA, confirm that, and then we'll do a crypto key zeroize RSA to get rid of the public-private key pairs. And then we'll generate a new public-private key pair with a 1024-bit modulus. And we'll say the label is going to be r2.cbtnuggets.com. And you'll notice the time is a lot faster with a 1024-bit modulus for the creation of those keys versus a 2048. I think previously it took like 6 to 8 seconds, and here it just takes a couple seconds. Next, let's reestablish that PKI trust point. We'll call it trusted-CA. We'll specify the enrollment URL. We'll specify the RSA key pair we want to use, which we labeled r2.cbtnuggets.com. We'll specify our fully qualified domain name, our subject name with the common name of R2 and the organization cbtnuggets.com. All of that will go into our certificate, and we'll say no to the revocation check. We also need to go ahead and authenticate the CA server again because we wiped out all of our keys. So we'll do a crypto PKI authenticate trusted CA. We'll say yes, we accept it. And then we'll go ahead and enroll to get our own identity certificate with the crypto PKI enroll and the name of our PKI trust point. We'll put in a password. We'll confirm it. We'll say no to the serial number, yes to the IP address, put in that IP address, and then say yes to go ahead and get our identity certificate. And now we have virtually the same configuration that we did over on R1. We're going to go ahead and create our certificate map. We'll call it CMAP here as well. We'll say we're looking for the issuer name that contains CBT nuggets as part of the issuer name. Next, we'll create our IKE version 2 proposal. We'll name it IKEv2-proposal, and we'll specify for encryption we want to use AES-128. For data integrity, we'll use SHA-1, and for Diffie-Hellman, we'll use group number 5. So we have compatible proposals on both sides. Next, we'll create an IKEv2 policy called IKEv2 policy that has simply in it that proposal that we just created called IKEv2 proposal. If we were using the defaults, the default proposal and the default policy are already linked together. Next, we'll create our IKEv2 profile. We'll call it IKEv2 profile over here as well. We'll specify the identity is the local distinguished name right from the cert. We'll match certificate called CMAP. That's our certificate map. The authentication for the remote and for the local will be RSA Sig. And then because we're not using a keyring, we don't need to point to a keyring. However, we do need to specify the trust point that we're going to use as part of this authentication. So that's PKI trust point and then the name of our trust point. We're going to create a transform set for IPsec that matches what we have over on R1, which is using AES-128 and SHA for hashed message authentication code. And the name of our transform set, we're calling it our-T set. We're also going to specify the mode of transport. Next, we're going to go ahead and create an IPsec profile. We'll name it IPsec-profile. And inside that profile, we're going to do two things. We're going to specify which transform set to use. That's the one we just created. And specify the IKEv2 profile to use, which is the one called IKEv2 profile. And then last but not least, we need to put this policy into gear. We need to apply that profile to an interface. Let's go ahead and use a tunnel interface with interface tunnel 0. IP unnumbered, pointing back to loopback 0. Tunnel source is Ethernet 00. Tunnel mode is IPsec IPv4. The tunnel destination is the reachable address of R1 at 15.0.0.1. And then the IPsec profile, we apply that with the command tunnel protection IPsec profile. And the name of our IPsec profile, we'll also toss this interface into OSPF process ID 1 area 0. Now this message right here is saying, hey, I got an IPsec packet, but I didn't bother de-encrypting it because the SPI was not correct for it. So this will clear itself up. IKE version 2 is a lot better at tunnel maintenance and keeping track of things compared to IKE version 1. Also, the fact that it says the adjacency came up with OSPF is a very, very positive sign that everything's working. Now, how would we verify that? We do a show crypto IKEv2 security association and take a look at the details. So the encryption for the IKEv2 tunnel is AES-128, hashing is SHA, Diffie-Hellman group 5, RSA signatures for the authentication, and that looks very positive. If we wanted to see more detail, we'd hit the up arrow key and simply add on the keyword detail and press enter. And based on this output, this security association, this IKEv2 tunnel, was not initiated by R2. So that means that R1 was the initiator of this tunnel, R2 was the receiver, and they were able to successfully negotiate, authenticate, and bring up the tunnel. Of course, we could issue the command show crypto engine connections active, and that'll show us the IKE version 2 and the children essays, specifically the IPsec essays. And I did notice that we had an OSPF neighborship that came up. If we do a show IP route for OSPF learned routes, we can see if we learned any routes via that neighborship. And it looks like we have. We can reach the 10.1.1 subnet, which is the network behind R1. And to verify reachability, we can do a ping to 10.1.1.1 and source it from 10.2.2.2 and verify that the connectivity works. And if we do the up arrow a few times for the show crypto engine connections active, it should reflect the additional traffic that's going back and forth. So even though we only did 5 pings, the other traffic that's going back and forth would be the OSPF hello messages, which happen approximately every 10 seconds in both directions. I have had a great time in this video. I'm so glad you joined me for it. I strongly encourage you to practice with the authentication of IKEv2 with site-to-site using RSA signatures. And to assist with that, in the Nugget Lab files, I've got the full syntax for what we did together in this video today, including the removal of the old trust point, the removal of the RSA key pairs, the regeneration of that, and then on to implementing the IKE version 2 and IPsec components to implement RSA authentication for the site-to-site tunnel. So again, I've had a great time. I'm so glad you joined me for it. I hope this has been informative for you, and I'd like to thank you for viewing.